Hi everyone. It is Wednesday, and I got a couple emails today saying that the video wasn't working, or the link wasn't there. And the video I originally recorded isn't making its way through the processing section of YouTube. I don't know what YouTube does when it processes the video before it publishes it. But for whatever reason, the first video that I made, the first recording of this lecture, never made it through, which I didn't even realize. So I set up the link before the video was fully published, so I didn't even know that it hadn't made it through. So thank you to those that emailed me. I had no idea, and I'm really sorry. I was trying to figure out all afternoon how to fix it, so I just decided to re-record and hope that a new video uploading will work. So I'll have it up later this afternoon. As soon as I'm done, I'll upload it. It takes a little while to upload and process, so hopefully it will go through this time. Unfortunately, the videos are way too large for me to post at all on Canvas or send in an email via Saddleback email. So YouTube generally has been pretty good for this. So sorry again for that delay. I know it's Wednesday. I'm glad that I give you guys the whole week so that those that were working on this early were able to let me know. So you should still have some time Thursday and Friday to finish the assignments and the homework. So we are going to be talking about the Big Bang for week 15. So let's get into it. For today, we're going to talk, you're going to learn about the Big Bang and the history of our universe. So there was the Big Bang, and then there were kind of 4 really important changes that the universe went through to get up until this point as the universe was cooling. You'll learn those 4 major changes. We're also going to go through the different types of models of the universe that are mathematically could work. There's 3 of them, and then I'll let you know which one we believe to be correct. There's a couple of problems with the Big Bang theory, but there's a hypothesis to explain it all away. So we'll go through that. And then we're also going to talk at the end about how the universe is expanding, how it has expanded, how the rate of expansion has actually changed over the age of the universe. And then we will look at the things that make up the density of our universe. So it's a little shorter. I think this is a little bit lower on the slide count number, but there is also a pretty cool video that I have linked at the end of the lecture. I'm not going to watch it with you on this video, but you should definitely take a look. There's some cool images and some nice interviews with some astronomers. I think the video is like 7 or 8 minutes. It's not long, but it's a really good one. So, cosmology is sort of a offshoot of astronomy in that it is the study of the universe itself. So cosmologists actually attempt to understand the universe. So the universe, how it formed, how it has changed over time, the structure, what it might look like. It's a very, very, very interesting science, and it is definitely a science where if you are the type of person that likes to know for a fact the right answer, this would not be the science for you. So there are a lot of unknowns, a lot of physics involved, but even with this lecture today, there's a lot that we don't know. There's a lot of assumptions and hypotheses and things that we think are correct and we're pretty sure. But as you can imagine, we are lacking a good amount of evidence. So what we know about the Big Bang, what we're going to be talking about today, what we know about our universe is just what we are able to say now, what we know of as of now. I'm sure in the future we will only be learning more and more and more about our universe. So some big questions that the scientists that study the universe ask are, does the universe have an edge? Does it have a center? How big is the universe? How is it changing over time? From what we know, the most modern observations of the universe show that we think the universe is infinite, meaning that it has no edge, it doesn't end, and that means that it also cannot have a center. So if there's no edges, there is no center. So that is what we think of our universe. It is infinite. There's no edge and there's no center. So something also really interesting about our universe that was actually discovered by Hubble, the Hubble telescope named after him, learned that cosmic redshifts are very, very important when understanding our universe. And the redshift of a galaxy is actually proportional to the distance. So galaxies that are close have very small redshifts. Galaxies that are further have very large redshifts. So this means that, we know that a redshift means things are moving away from each other. But this change in redshift, meaning close galaxies have small ones, larger galaxies have larger redshifts, tells us that the universe actually is expanding. So we're going to get into galactic redshifts about halfway through the lecture. These are sort of the most important components of modern study of the universe. So the Big Bang. The Big Bang is a theory that, a scientific theory of how the universe began. The issue with the name the Big Bang is that it was named when people believed that the Big Bang was a sort of explosion, which we now know is not quite correct. So the Big Bang makes you think that there was some explosion in or from somewhere. There's a single point in space that exploded. We don't believe that to be true. So the Big Bang, it didn't actually originate from one spot. They say, I like the way the textbook actually said the best way to, if you had to rename the Big Bang, they would rename it the Big Stretch, because everything filled the entire volume of the universe all at once, and it has now since been constantly stretching. So the universe, it began at a moment of very extreme conditions. We know that. We don't know much about the very start. So we know about right after the very, very start, but we really don't know much about how it actually all started. But we do know that all of the matter that's now in our universe was all merged together, all very, very, very compressed to high density and high temperature as this Big Bang occurred. So the way that we can observe anything about or close to the Big Bang is looking at look-back time. So looking at things where we know it's very, very far away, so we're observing something far, far back in time. So when we talk about stretching and expanding of the universe, a good analogy is to think of raisin bread. That's what this picture is here. So the raisins themselves are not really being stretched. It's that the bread is growing, and it's growing in all directions. So as your bread or your dough of your raisin bread rises, your raisins are going to be carried further away from each other. And the distance is proportional to the distance that they started out. So you'll notice these two raisins are closer together than these two raisins. In the end, once the dough has risen, or as the dough is rising, still these two raisins are closer together than these two raisins. So the expansion, the distance between, or the distance that, the expansion of the distances, is proportional to the distance at the start. So these two were closer together, so it's not going to expand quite as much as these two, which were very far apart here. So the expansion, or the change in their distance, is much more extreme. So that is sort of what happens as the universe is expanding. It's sort of a stretch of space. It's not necessarily a stretch of every single object, and it's fairly proportional. So, like I said, the very beginning, we don't know. So So the very, not a very satisfying answer, but the very, very beginning, time zero of the universe, of the Big Bang, we do not know. We do not have this physics, or we don't understand the physics. We haven't figured out the physics of those incredibly extreme conditions. But we can come pretty close. So astronomers have determined that within about 1 times 10 to the negative 7 seconds, so that's this here, 0.0000001 seconds, that's when we start our understanding of the universe. So that's pretty close to the beginning. It's less than a second after the Big Bang, of course, significantly less than a second after the Big Bang. We can say we know some things about the universe, but it's that very, very beginning, that time zero, that we just do not know. So we know that at the very fraction of a second after the very start, the universe was filled with very, very high energy photons. So in the gamma ray wavelength, the highest wavelength, and the temperature was about 20 trillion Kelvin. Very, very, very hot. So at this point, photons can combine. So photons, they're so hot that they can actually combine, and they create a pair of particles. So these particles, they create one particle of normal matter and one particle of antimatter, being antimatter is sort of defined as what is produced along with normal matter. So we're not going to get into that too much. You don't have to worry about explaining antimatter too much, too chemical for this class, but you'll just have to know about this cycling. So then we have matter particles and we have antimatter particles. So then what happens is a matter particle and an antimatter particle can combine. They actually will destroy each other and then convert into gamma rays. So there was this cycling of gamma rays creating particles, particles creating gamma rays creating particles, particles creating gamma rays. So what this means is our universe in the very beginning was actually flickering. So it was flickering from these photons. So from these gamma rays forming and then combining and destroying and forming and combining and destroying. It was all flickering. So all of these particles from photon to particle and back to photon to particle. The early universe we know was incredibly hot and flickering with light. The light would have been all in the gamma ray. So not visible light, but gamma ray. So what happened is almost all of the antimatter was actually destroyed in this process. A very small amount of regular or normal matter remained, which is why everything that we have now, our world, is made of normal matter. So matter that we have today was formed or began at the very, 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 very beginning of our universe. So in the first few minutes, all of the protons, the neutrons, and the electrons were formed. So all of our protons, neutrons, and electrons in the universe were formed in the first few minutes of the universe. So nuclei couldn't form until about 2 minutes. So the universe was too hot. So very, very high energy photons, all of those very hot, high energy gamma rays were too hot to allow for nucleization. So the nuclei would just be broken apart. So by about 2 minutes, the universe had cooled slightly for nuclei to actually form. So by 2 minutes, we had nuclei. And then by 3 minutes, the universe was actually cool enough that almost all nuclear reactions stopped. So by 3 minutes, almost all of the nuclear reactions in the universe stopped in just 3 minutes. And then by 30 minutes, we're pretty sure that all nuclear reactions stopped completely. So after 30 minutes, the universe had cooled enough for all nuclear reactions to stop. So at this point, the universe, the mass is about 3/4 or 75% worth of protons. They were all hydrogen nuclei. So about 75% hydrogen nuclei and then about 25% helium nuclei. So this is the same composition that we find in our very oldest stars, because these stars were made from this hydrogen and helium that was available at this time. So it's interesting that we have evidence of that 75%, 25% in our very oldest stars. So the universe, it started with those incredibly high energy photons. And as the universe aged, it cooled. So there's 4 important changes that the universe went through as it cooled. So we're going to go through those briefly. At the age of about 50,000 years, so after about 50,000 years from the Big Bang, the universe cooled enough that matter was actually able to clump together. So matter was able to stick together. It was cool enough that matter could stick, which means that clouds and galaxies could start to form. So this allowed for the formation of clouds of matter, things to actually grow in size and in mass. And at this point, the density of gas became more than the density of energy. So this was the switch between our universe being almost completely energy, in the term of our universe was almost completely photons. Now our universe became more mass than energy. So it was actually more gas than there are photons in the universe. So after about 400,000 years, so remember, this is not on a regular time scale. So we're talking when matter began to clump, it was about 50,000 years. So now, now we're jumping to 400,000 years. So after the 400,000 years after the Big Bang, there were all of the free electrons in the universe were so far apart by this point that photons could travel for thousands of parsecs before being intercepted by an electron. So before being absorbed and emitted, there was so much space in between each photon that in between each electron, that these photons didn't actually produce much light because they were rarely running into anything. So this is when our universe began to actually be transparent instead of glowing. So at about 400,000 years, things were so spread out that the photons had plenty of space between each electron. So our universe began to actually be transparent. So around this same time, so 400,000 years, when the universe cooled to about 3,000 Kelvin, is when protons were able to capture and actually hold on to free electrons, which means that we were able to form hydrogen. So this is what we call recombination. So this is when it's cool enough for protons to actually be able to capture those free electrons. So recombination is when we started to form hydrogen in the universe. So this is when the gases in our universe became completely transparent. There was no more interaction with photons. So what happened next, for the next about 400 million years, as the universe continued to cool and expand, we call this the Dark Age. So this is when all of the glow from the warm gases actually faded and cooled. So as everything is cooling, imagine it's all dropping through sort of the electromagnetic spectrum. So the universe cools enough to the point where it's glowing in the visible. And then as it continues to cool, it's no longer glowing because all of the gas has actually faded into the infrared wavelengths. So after that point, we call this the dark age, when the universe became dark. So the very last important change is when the first stars were born. So this was at the end of the Dark Age. So the Dark Age lasted for about 400 million years. That's here. And then afterwards, the last important change is that stars began to form. This ended the Dark Age because stars, of course, produce light. And the first bursts of formation of stars actually produced enough UV light to then ionize and excite nearby gas. So it was sort of a domino effect. So we call this the reionization era, when things began to become reionized, starting the formation of stars and also galaxies. So this ended our dark age because, again, we had light from these stars and from these early galaxies. So here's a nice NSF image, a timeline. So we have universe at age 0. This is our Big Bang-ish. Of course, this is not really what it looks like. This is just a drawing to try and conceptualize. And you'll see reionization here. Here we have galaxies. Here we have now at the end. So if we think about the Big Bang and the age of our universe in a graph, notice this is not a linear timeline down here. You'll notice that as temperature cools over time, it cools pretty quickly in the beginning. And then this line is where we have our universe switching from a radiation-dominated universe to a matter-dominated universe. And then we have our recombination and our reionization, the first stars and galaxies. This is that time, remember, when things were able to clump together. So matter, an actual gas, became more of our universe's density than the photons and the radiation. So if you're a graph person, I like this graph a lot for thinking about the universe in terms of the early universe and how it aged. So the next important topic when we think about the universe, I mentioned this at the beginning, is what we call the cosmic redshift. So the cosmic redshift is how we know that the universe is expanding. So if you remember, a couple of weeks ago, we talked about space-time and Einstein's idea of space-time. It is the combination of space and time into its own dimension. So when we think about the expansion of the universe, we're really thinking about the expansion of space-time in terms of we're stretching it sort of like rubber. So they astronomers often compare it to stretching rubber. So galaxies really are at rest. They're motionless in space-time, but they're being carried away from each other by the stretching of space-time itself. So the galaxies aren't necessarily moving themselves, but they're being pulled apart because space-time is stretching. It's a little difficult to, it's very, very difficult to conceptualize, I should say. But what happens as this stretching occurs is we are expanding the path that the photons will travel. So we're actually stretching, the universe is actually stretching out the wavelength of the photons. So the photons, as they are moving, so if we have a photon moving through the universe, say, towards Earth, it's actually being stretched out. So we see an apparent redshift as it moves through this expanding or this stretching space-time. We see a redshift because the wavelengths themselves are being stretched. So photons from very, very, very distant galaxies have to travel much longer to get to Earth. So they will be stretched much more because they're spending much more time traveling through this expanding space-time. Galaxies that are closer aren't going to have as significant of a redshift because they aren't stretched for as long or as much of a distance. So we learned that the redshift that we see actually depends on distance. So this, here is the a figure from, I think this is from our textbook. Yes, I'm pretty sure. I like this figure. It breaks it down sort of step by step. So you'll notice in these figures, here is our photon traveling from this galaxy. But as time goes on, so as this photon is moving from the right to the left of this figure, notice that the grid on the background is expanding because we're stretching. We're actually stretching the space-time. So we are stretching space-time as this photon is moving, which means we are also stretching out the wavelength of the photon. So the photon starts in the purple, then it gets shifted more towards the red into blue, more towards red into yellow, more towards red into red. So we see that shifting. You'll notice, of course, here has a shorter wavelength than here when it's red. So as the photon is moving, the length of the wavelength, the wavelength actually increases. So we end up with a redshift. And the amount of redshift depends on how long the photon was traveling through this stretching and expanding space-time. So when we think about the universe, there are 3 different models or ideas of the universe that mathematically could be possible. So one is that the universe might be flat, and then there are 2 different curved options that mathematically could make sense. Our current and most modern understanding is that the universe is flat. It's pretty certain. They say it's almost certainly correct, the flat model of the universe. So I'm going to go through all 3 just briefly. So the first is to think about a closed universe, and it has a positive curvature, and it curves back on itself. So the example that our textbook uses is an ant on an orange. So if you picture a 2-dimensional ant on a 3-dimensional spherical orange, the ant does not have any idea about up or down. So it can't jump and it can't dig down into the orange, but it can walk, in any direction. So it's 2-dimensional, this ant. So the ant can walk all over this orange, and there is no edge to the ant. There's no edge to this orange, which means there is also no center. Because it's 2-dimensional, we know in 3 dimensions there is a center in an orange. But to this ant, there is no edge and there is no center to this orange, to this 3-dimensional universe that the ant is living on. So it's sort of like a sphere if you were then in 2 dimensions. So that's what we mean by no edge and no center. So that is the closed universe with a positive curvature. The other 2 are open universes. So open universes are space-time itself is curved, but it's not curved all the way back in on itself like a sphere. So this is no center and no edge, and they expand forever. So they are infinite. They don't have any end, but they do not curve back on themselves the way that the closed does, like the orange. So the flat universe, this is the one that we think is correct. The universe is not curved, but it is infinite. There's no edge, there's no center, and it expands forever. But it is completely flat. There's also a negatively curved or saddle-shaped model of the universe, where circles, if you were to draw circles, they're actually stretched because space-time is stretched in certain directions. So because we don't see that, we do think that the flat universe is the most correct. So I have some evidence that we'll go over of why we think the flat universe is correct. So something really important when we think about the universe is the density of the universe. So what we call the critical density is the density of the universe, or the density that the universe would have to be in order to stop expansion. So if the density of the universe was equal to the critical density, space-time would be completely flat. So the open model, open model of the universe would contain less than the critical density. The closed model would contain more than the critical density. So if our universe is flat, then the density of the universe must equal this critical density, which is this value here. The problem is that when we calculate the density of our universe using all of the matter that is detectable, it only comes up with about 5% of our critical density. So that doesn't quite make sense. What else makes up that other 95%? If all of the matter in the universe only makes up 5% of what we are expecting, what else is there? So one of the answers is what we call dark matter. So there is proof using specific elements that normal matter, what we call normal matter, so what we are made of, for example, makes up only about 5% of our critical density. Dark matter, which is matter that does not interact with electromagnetic radiation at all, so no light, it is undetectable. We know that there is evidence for a lot of dark matter in our universe. However, it is undetectable. We do know that it exists. We know that it is there. So factoring in this dark matter, which we call dark matter because it doesn't interact with light in any wavelength, looking at all matter, so both normal matter and this dark matter, it only makes up about 30% of the total density of our universe. So we're still missing about 70% of the density of our universe, and we've already taken into account all of the matter, even the matter that is undetectable. So we'll get to that in just a minute. We are pretty sure we know what makes up that 70%, but it's coming at the end of the lecture. So our Big Bang Theory, there are a few problems. There are two problems, actually. Two big ones that we're going to go over today. One is called the flatness problem. The other is the horizon problem. So the flatness problem is, why is our universe so close to perfectly flat? How is that possible? That the universe just happens to be so perfectly close, so incredibly close to being perfectly flat. It seems very strange that the universe could be anything and it ends up having the density, almost exactly the density, what it would take to be a flat universe. So there's our first question. The second one is called the horizon problem. So this is, how is everything in the universe the same temperature? So how is it possible that every single part of the universe became the same temperature? When recombination occurred, this is when the gas started to become transparent. The universe wasn't exactly old enough for energy to travel from one region to another region, so there would be no mixing. There wasn't enough time at this point for two separate locations to exchange and equalize their temperatures. So according to this original Big Bang Theory, it doesn't make sense that the universe is essentially all the same temperature, or so evenly spread in terms of temperatures. Because back in early formation, at the time of recombination, there wasn't enough mixing going on. Two separate spots in our universe wouldn't have had the time in terms of age to actually mix, to exchange, to equalize temperatures. So these are the two big problems, the standout issues with the Big Bang Theory. And the hypothesis that sort of explains them all away is called the inflationary universe. So astronomers are pretty certain that when the universe was very, very young, not at the very beginning, but when the universe was quite young, that there was a huge, enormous expansion that happened very suddenly, and they call that inflation. So that's why it's called the inflationary universe hypothesis. So this is actually thought to be much more extreme than we originally thought about the Big Bang. So this is actually thought to be a huge, enormous expansion, much more extreme than the Big Bang itself. So this helps us with our understanding of these Big Bang problems, because the sudden inflation would have actually forced any curvature in the universe to be almost zero. So a huge, unbelievable inflation all at once would have expanded the universe so quickly that it would have a curvature value of almost zero, incredibly fast. So almost like if you have a balloon, and as you inflate the balloon, the regions on the balloon become more and more flat as you inflate the balloon. So imagine if you could inflate a balloon to gigantic proportions without the balloon popping. You could inflate it to the point where the regions, like two regions next to each other, would seem very, very, very flat. Something similar to that. So that sudden inflation that happened very quickly would have actually almost flattened out all of the curvature that the universe may have had initially. The other thing to think about is that the universe was absolutely tiny beforehand. So before this inflation, the universe would have actually been incredibly small, which means that it would have had enough time to equalize temperatures, to equal out, to become sort of an equilibrium temperature before this inflation occurred. So if we think about the size of the universe jumping at this inflation, that means that in the very beginning it was significantly smaller. So it actually was able to equalize its temperatures before the inflation occurred. So that explains how two incredibly distant areas actually were mixing earlier, because they were so much closer together before this inflation period. So the Big Bang does pretty well explaining the universe that we know of, but it was really that inflationary hypothesis that sealed the deal and made those two big issues with the Big Bang sort of disappear. It really explained away the two big problems with the Big Bang Theory. So our universe is expanding. You may have heard this before. And it's a little bit strange. So the theory of relativity says that as galaxies are moving apart, the expansion should actually slow, because gravity is trying to pull galaxies back towards each other. But evidence actually shows that our galaxy is expanding and it is not slowing down. So scientists, astronomers have actually used supernova as distance indicators to test this. So they showed that these distance indicators were about 25% fainter than they expected, meaning that they were further away than mathematically predicted. Further away than expected, which means that this expansion of our universe actually is not slowing down. So the expansion of the universe is not slowing down, as the theory of relativity states. It's actually speeding up. So how is that possible? We just said the theory of relativity says that gravity is going to try and slow down the expansion of the universe. So what do we have that is actually outweighing the force of gravity? What is outweighing what we expect of gravity? We call it a force of repulsion. So there must be, the main answer is we don't know, but we know, we can guess. So we know that there must be some force of repulsion acting in opposition of gravity. So there must be a force that is actually causing acceleration of the expansion of our universe, which can outweigh the expected gravitational force, which would cause the universe expansion to slow down. So this force is some sort of unknown energy that is all throughout space. Because all throughout space, the universe expansion is speeding up. So there is some force outweighing what we thought in terms of gravity. So there's some force stronger than gravity allowing our universe to continue expanding and actually expanding at an increasing rate. So we call this dark energy. So dark energy is what we call this force that actually drives the acceleration of our universe. So it allows for our acceleration, it allows for our universe to continue expanding and also increase the rate of expansion, but it does not actually contribute to the formation of stars in any way. Dark energy is what we call this force of repulsion. So our universe has not always been expanding. At the start, galaxies were actually very close together because our universe was much smaller then. The gravitational pull would have been a lot stronger, and it would have been actually stronger than the effect of dark energy. So our universe has not always been increasing in its expansion. At one point, in the beginning, gravity was actually stronger than the effect of dark energy. So dark energy is really interesting because it has helped astronomers understand the curvature of the universe, understand the expansion of the universe. We've actually been able to determine that dark energy is what makes up that extra 70% of our universe's density. So remember we said that normal matter and dark or undetectable matter make up about 30% of the universe's density. Astronomers believe that it is the dark energy that makes up the rest of the universe's density. So our data and our observations show that our universe is flat, it is accelerating in expansion, and it will expand forever. And the universe's age is about 13.8 billion years old. The universe contains about 4.5% normal matter, which is what we're made of, 22.7% dark matter, and 72.8% dark energy. So that dark energy, that repulsionary force, makes up about 2/3 of the density of our universe. So what we actually can see and observe is only about 4.5% of the density of our universe. So here is a link to a video that I highly suggest you watch. The Big Bang and the expansion of the universe is not something that, it's not an easy concept. There's a lot that we don't know, and to only get into it with one short lecture for this class is not doing it justice. But feel free to take further astronomy classes if you're interested. This is a really good short video if you want to learn more. I highly suggest you watch it. It's a really good one. And there are 2 assignments, like always, and then 1 homework. I think the second assignment is a bit shorter, but they are all generally pretty short. So we will pick up from where we left off today. Next week, we will continue talking about the universe. And then our last week or 2, we'll talk about our solar system specifically. So good luck with the stuff today, and I really hope this video uploads to YouTube correctly. So we'll see. Hopefully, you will all be able to watch this video in an hour or so.